Okay, so this worksheet we just did, my hope was that you could see how the math and the concepts went together hand in hand. Like I tried to really intentionally tried to like drill in these concepts. Okay, today's lesson and the worksheet you have for homework due on Monday is going to be the same stuff. The only difference is we're going to be incorporating that momentum is equal to mass times velocity. That is it. It's just going to be a little bit more mathy, but not much. Okay. So we're revisiting the bowling ball, bowling pin collision. I'm giving you some numbers. Okay. So the first thing we do is identify what objects need to be in the system for momentum to be conserved. Obviously, we've talked about this enough. Bowling ball, bowling pin. Okay. The second thing I need to do, and this is like crucial, is I need to figure out, I need to determine which direction is going to be positive. Okay. So the numbers, the measurements. So let's say the bowling ball has a mass of 7 kilograms initially, the velocity of 2 meters per second to the right. So it's like rolling slow. It's a slow roller. The bowling pin has a mass of 4 kilograms and initially at rest. Right after they collide, the bowling ball is now moving at 0.25 meters a second to the left. So it was rolling slow enough that when it hit, it bounced backwards. How fast is the pin going and in which direction? Okay, so I need to specify which direction is positive. I'm going to make to the right positive because that's the way things are moving initially. Okay. Now, I've determined that momentum is conserved. So the momentum of the system initially of the bowling ball, bowling pin is going to be the same as the final. The momentum of the system is the ball and the pin. So I've got the ball's initial momentum plus the pin's initial momentum. That would be the momentum of the system. Is equal to the momentum of the ball final plus momentum of the pin final. That's the momentum of the system afterwards. This is what you did all over the place on your worksheet that was due today. Okay. I just gave you the momentums. Okay. But now we need to remember that momentum is equal to mass times velocity. Okay. So the momentum of the ball initial, it had a mass of 7 kilograms and it had an initial velocity of 2 meters per second to the right. Now, velocity, does it have direction? Yes. Does momentum have direction? Yes. Okay. If I give you a number, a value for anything that's a vector, momentum or velocity, you must assign a positive or negative sign to that. Have to. Okay. It is moving to the right. I've determined that right is positive. So that's a positive 2 meters per second. Now, I recognize that you don't have to put that in there before you get to the right answer. I'm just trying to teach it well. Okay. What is the momentum of the pin initially? 0. It was not moving. The momentum of the ball final, it still has a mass of 7 kilograms and is now moving at 0.25 meters per second to the left. It's a vector, it's a velocity, it has direction. I need to assign to that. Left is negative right there. That is why you're going to miss or get this problem right. That detail right there. That is as hard as it gets. Okay? You remembering to put that. Okay? Afterwards, the momentum of the pin has a mass of 4 kilograms times some final velocity of the pin. If you are looking for something, if you're trying to solve for something, do not assign a positive or negative sign to that. Only assign positive and negative signs to things that you have values for. Good with that? And that's the setup. That's as hard as it gets. Okay? The math in this unit is easy. There's just bookkeeping to do with assigning positive and negative directions. Okay? So you get 14 is equal to negative 1.75 plus 4v. 15.75 4v, and that is equal to 3.94 meters per second. The sign of that is what? Positive. Here's going to be your answers on the multiple choice. It's going to be 3.94 meters per second to the right, 3.94 meters per second to the left, and then I'll have an answer calculated if you forgot that negative sign. Let's say it was 6 meters per second to the right, 6 meters per second to the left. That's what your choices are going to look like. Okay. It turned out positive, so that means it's going which way? To the right. Does that correspond with what do you expect to happen? Yep. Good with that? But make sure your math is backing you up. Good with that? Questions there? Okay, follow-up question. Is the velocity of the system conserved? Is the velocity of the system conserved? Tell your neighbor. What do you say? Is velocity conserved? Here you started with 2. At the end, you had negative 0.25 and positive 3.94. There's more velocity than when you started with. Velocity is not conserved. Momentum is. Okay, good with that? That's a pitfall that I've seen people fall into. Okay. Any questions here? Okay, so in case you forget, this is the recipe for making conservation of momentum problems work for you. Okay, so if you get stuck, refer back to that. This is on Canvas. It's on video. Get options. Okay. Another example. Big fish, 5 kilograms, is swimming at 6 meters per second westward towards an absent-minded, smaller 2-kilogram fish swimming at 3 meters per second eastward. When the 5-kilogram fish swallows the 2-kilogram fish, what is the 5 kilograms fish's velocity immediately after lunch? So let's just put this out on the table. Dory would not make it past childhood. Like, sorry. So we got to figure out, okay, what objects would you put in the system for momentum to be conserved? 2 fish. Okay. So we are saying that the momentum of the system initial is going to be equal to the momentum of the system final. Okay. Now, I need to make a direction positive. Okay. If I was in your shoes, I would make west positive. Okay. That's probably which way it's going to end up going at the end. But just so that I can teach something, I'm going to make east positive. Okay. There's not a wrong or a right way to do it, but I'm going to make the positive direction to the east and negative direction to the west. Okay, again, if I was doing this, if I was doing this by myself, I would make west positive. Okay. So you've got the momentum of the big fish initial plus the momentum of dory initial is equal to the momentum of the big fish final plus the momentum of dory final. Good with that? Okay. The momentum of the big fish initial is 5 kilograms times a velocity of 6 meters per second westward. That's essential. Okay, you have to determine that. Plus Dory's momentum, you have 2 kilograms, the mass times the velocity of 3 meters per second eastward. That's going in the positive direction. Good with that? Equals the momentum of the big fish final. So you got 5 kilograms times some final velocity plus Dory's momentum final. So question, does Dory have momentum after she's eaten? More specifically, does Dory's carcass still have momentum after she's in the stomach? Okay. Everybody like engaged in that question? Okay. So just keep swimming, swimming. Does Dory's mass still have momentum after she's eaten? Just keep swimming. Okay. If you said no, here's what would have to happen. Just keep swimming. So either the fish, the big fish, would have an amazing digestive tract, or we just blew the tail out of the big fish. Does that make sense? Does Dory's body still have momentum? Yes, it's riding along in the big fish's stomach now. Does that make sense? Okay. So, how fast is it going? So I've got 2 kilograms. What's the velocity? of Dory's body now? Same as this, right? As a big fish. So you could either consider it like this, or you could consider it as the big fish with a full stomach. Does that make sense? Either way is fine. Okay. So, solving for this, get negative 30 plus 6 equals 7. That's negative 24 divided by 7. You get a negative 3.43 meters per second. So the answers on your multiple choice test are going to be 3.43 meters per second east, 3.43 meters per second west. And then if you forgot to do the negative signs here, you're going to make this number up. 2 meters per second east, 2 meters per second west. Those would be your choices. That's where you like mess up. Okay? So, looking at your answer, the negative sign corresponds with what? Westward. Okay? If you would have made west positive, this would have ended up being positive, and you would get a consistent answer of west. So which way you make positive and negative, completely up to you. You just have to be faithful to stick with it. Okay? Assigning positive and negative is when you have numbers. Do not assign a positive and negative if you're solving for it. And the answer will show you which direction it's moving. If it ends up positive, that's the positive direction. If it ends up negative, that's the whatever you made the negative direction to be. Good with that? Okay. That's as difficult as it gets. Okay. I make that sound easy, but for some reason that's challenging for you guys to gauge it. Okay. Questions there? One last question. Have a conversation.
Is it assuming that they stay together and keep going?
Correct answer is? Correct answer is the same. Why? They stick together. Good with that? Okay. Got a worksheet due on Monday.